we're all set to go. Okay, so let's move on to talk about the vapor liquid equilibrium. So that's our lecture 20, and that part will be also a core part of this coming unit exam 4 next week. So first of all, as I mentioned in the email, I'm trying to put together some interesting examples so that you guys can review and prepare yourself for the coming exam 4. So for instance, if we have a problem like this, comment. So if we have a problem like this, looking like we need to calculate the activity coefficient over here. And first of all, this is not a typo. I don't have typos sometimes in the exam or in the homework solution, but here is exactly what we try to have. So this is the Margaret's equation, and activity coefficient is expressed as a function of the liquid composition. And we need to figure out the activity coefficient for the component 1. So if you have a problem like this, I hope that you recall, first of all, the very general equation, the magic equation we have, which is if we look at the general case, starting from the fugacity in the liquid and vapor phase, and I hope that you are able to move on to look at that the most general case would be x1 activity coefficient. I'm using I, and then this is a pi set. This is for the liquid phase, right? For the vapor phase, that would be the yi. For the fugacity coefficient, find I, and then this is p total. So for any system, we should be able to write down this equation and move on. Okay, so this is the first thing, and that's actually explain why we are interested in those activity coefficient models. So for the specific question over here, then if we need to calculate the activity coefficient value for component 1, then we need to know the x1, which is good. We are provided with x1 value. So if we somehow plug into one of the Margaret's equation, then we are able to calculate, but we need to figure out the a value. So the a value is not provided, and we need to figure that out. So in order to figure out the a value, then we need to set up the equation for the component 1 and component 2. Okay.
Okay.
So that is something we need to figure out, and probably we need to look at that from the problem statement. We know the P1 set, we know the P2 set, and if I know the X1, then I shall be able to know X2. So then you need to think about how I'm going to look at the general equation, try to simplify from there. And then there's one other condition says, well, the gas phase is treated as the ideal gas, which means I can simplify the general equation to xi. This is still pi set. Now on the right hand side, I should be able to simply use yi p total. All right. So I hope that by some examples, you sort of develop the idea that we typically write down this as x1, p1 set, y1 p total, x2 activity coefficient of the component 2. This would be y2 p total. While in this problem, we don't know x1 and x2. Well, it's actually provided, sorry. Yeah, the problem statement actually provided. This is the special point at the azeotrope. But no matter how, if we try to combine the two equations, if we're mostly interested in the x1, we can easily get rid of that y values. And we will talk about those techniques in a few minutes. So if we will add the two equations on both sides. That would be y1 plus y2 p total. And that is simply 1, right? So by using this type of techniques, we should be able to get rid of the y1 and the y2. So now if you try to look at that simplified or modified equation, we know x1, we know x2, we know p1 set, we know p2 set. This is provided as a problem statement. P total is also known. And then we are having the equation of the activity coefficient. And the activity coefficient could be expressed by the two equations over there. So in the end, we are going to set up the equation involving only the unknown parameter capital A. Okay. So from there, we calculate A, and then we plug in the other values. We are able to solve for the part A. And now, if you have the expression for the A value, then for part B, if we need to calculate the dilute activity coefficient, for the dilute, we just need to push some value to 1 or 0. Okay. So if we try to calculate the component 1, then the dilute means x1 goes 0. Right? So if you have the general expression of the activity coefficient of 1, try to push that to the limit, then you should have this. Right? And then, of course, the total pressure can be also calculated very similarly if you know everything about the coefficients. So this is the problem 3 we had, and try to double check the solution I have from that year. Let's move on to the second problem. Second problem is a quite typical problem of the Gibbs-Duhem equation, as we have in the providing supporting information. So the problem itself says the partial molar volume of a binary mixture of ethanol and ethylene glycol at 25 degrees C is following this equation, right? Unit may be important, we'll see. And so we know this V1 partial molar volume. So if you look at that, I hope that you quickly recall the two equations. So this is involving V1 partial, this is V total, and then knowing one to calculate the other, V1, V2 partial. Sometimes we are also interested in the V1 and V2 of the pure, okay? So here it says in part A, what is the volume of 1 molar of pure ethanol? So this is component 1, component 1. We're interested in the V1 basically, right? So if we have this partial molar volume, and if we are interested in the V1 pure, then simply push this to x1 goes 1. Okay, then this V1, when x1 goes 1, this should be V1. Then you should have the answer of part A. The second is if 1 mole of pure ethylene glycol has a volume, well, this is V2, V2 of the pure. Then we need to calculate V2 partial. So there you need to think about how I'm going to come up with the equation. So potentially we could have two different equations to calculate V2 partial. Okay, the first one is if we stick with the Gibbs-Duhem equation, this will tell us x1 dv1 partial would be the same as x2 dv2. All right, so that may be one useful equation because we know x1 and the the connection with x2. So we can simply write down this as 1 minus x1. And we know dv1 partial. We have the expression for v1 partial. So take the full derivative, then this would be simply dv1 partial, simply would be negative 2.08 multiplied by 2 x1 and plus 4.16, right? So then you plug in, then you try to solve this dv2 partial as a function of x1, all right? But we are not interested in the full derivative of the partial molar volume. We are interested in understanding this v2 partial. So there we need to run the other step to run this integration, okay? So this is still fx1, dx1. This is dv2. Then we know that the final is any condition of x2 and the corresponding v2 partial. So this is the x1 to somehow convert the x1. x1 is 1 minus x2, so we need to keep that in mind. And then we need to somehow utilize this pure v2. Pure v2 means x1 goes 0. So if this is 0, then this corresponding would be the v2 pure. All right. So over there we are going to have no, this is dv2. This is v2 partial minus v2 of the pure should be some expression. And v2 is just a value we have from the problem statement. Okay. Then the third would be the mixing process. All right. So if we know the v1, v2 of the partial, v1, v2 of the pure, then the mixing should be x1, v1 partial plus x2, v2 partial. This is the mixture volume minus x1, v1 plus x2, v2. Right? So this is how we are going to calculate the mixing. So that is the second problem I want to quickly review. So far, any question?
Not from me.
Good, thank you, Connor. All right, if not, let's move on. Try to take a look at the other problem. So it says we have the excess Gibbs energy for liquid argon and the methane mixture. And we have this GE over RT as the expression of the argon and the methane liquid composition. And we have some other information. So the A and B coefficients, once we know the temperature, we're able to figure out the AB values. So that would be the known value to us if we know the temperature. So part A says derive. I don't want to emphasize that this is not asking you to somehow prove some equation. This is to ask you to calculate. I could easily use the calculate in order to avoid the discussion of, hey, this is the pure math problem. That's not. So we shall have those kind of problems in this coming unit exam. So now if we need to figure out the activity coefficient for argon and methane, so this is asking us to calculate the activity coefficient of argon and activity coefficient of methane. Okay. However, we don't have anything. We only have GE over RT and sun temperature, right? So how do we start from there? Well, if I don't know anything from the problem statement, then I need to figure out the connection. There will be.
Could
Yep.
I ask a question?
Sure.
In this case, would the temperature range be somewhat valuable, since we know it's a 7 degree, 7 Kelvin difference, or not really?
Uh, I'm not sure if you are still asking the question, but the problem statement says that between the temperature range, A and B should be able to calculate using the two equations provided. So for part A, this is a general expression for activity coefficient. Uh, so if this is the case, we just follow uh, the very general note of A and B. We don't have to manipulate the temperature because there's no temperature involved in part A. But in part B and C, we shall plug in the temperature and receive the AB values.
Okay, thank you.
Yeah. So now if you think about the activity coefficient, looks like the problem statement did not say anything about it. So what we can do? Well, then the only thing is we need to figure out what is the connection between the activity coefficient and GE over RT. Okay. So if you think about the previous slide and we discussed the partial molar property, so there we have the solution. So if we recall, we have two unusual pairs of the partial molar property, right? First one is the activity coefficient is corresponding to, excuse me, partial molar property and the property of the mixture. So we have this pair as a partial molar, which means the activity coefficient is described by GE over RT at fixed temperature and pressure. All right. So this is the pair we have. The other pair we also discussed is activity coefficient multiplied by the liquid composition. Then this is what's the correspondence? This is delta G over
Delta
RT.
G?
Thank you. Great. This is delta G, and then very similarly, we shall be able to figure out Xi still using the definition delta G over RT. Okay. And move on. So that is the third type of question I could come up and test the class on the understanding. So this is simply utilizing the partial molar property definition, and you need to recognize the corresponding pair. And that's only two pairs, sort of a little bit strange by looking at the equation. All right. So coming back, if you look at the previous problems, nothing special. We are always looking at the understanding of this equation. This is a very important one of the universal equations in thermal. Then the other is we try to look at the limits, pushing x1 goes to 0, pushing x1 goes to 1, and we have this dilute coefficient, or we are going to have the pure property of the component. All right. So that's the three examples I want to quickly revisit. And now if we move on, if we try to recall what we were talking about last lecture, we started some discussion of the vapor liquid phase equilibrium. We understand the three different type of calculations. So if I have a binary mixture and here using the example of liquid vapor equilibrium, then the first equation is the most simplified one. I hope you recall this is this is always for the vapor. This is always for the liquid on the And then at equilibrium, we should have this fugacity of the mixture in the vapor should be exactly the same as the fugacity of the mixture in the liquid, right? So we move on, try to look at the problem statement, see what equation will be the working equation for this specific problem. So if we are trying to treat this as the vapor phase as the ideal, excuse me, as the ideal gas phase, then uh, this should be the low pressure uh, ideal gas equation, right? Then for the liquid phase, if I'm going to use simply the saturation pressure and try to look at the liquid composition, then this is ideal solution. So if this is the case, then I should have low pressure and ideal solution. Okay, ideal solution means for the gas phase, it's ideal gas. For the liquid phase, all the intermolecular interactions are very similar to each other. So this is the first equation. Then moving from the first to the second, we are treating the gas phase exactly the same as the ideal gas, but the liquid phase is no longer ideal solution. So we are going to still have the low pressure or high pressure. But the problem statement has to say that the gas can be treated as the ideal gas. Okay, so that really depends. If I don't say anything about the gas phase, how you are going to treat it, but I say this is low pressure, then automatically you are going to treat this the ideal gas. If I say that this is relatively high pressure, but we can treat the gas phase as the ideal gas, then it's still a good equation to go for the gas phase treated by Yi P total. And for the liquid phase, then over here I don't need to have any assumption. So that could be the any liquid phase non-ideal liquid solution. Okay, so we start from the very general definition of the fugacity and utilizing the activity coefficient to deal with the liquid phase. The last case would be the most complicated, the most general case that we discussed. So there we don't need any assumption of the ideal for both liquid and vapor. So we always start from the coefficients and we try to figure out from there. So that is a little bit time consuming. We need to calculate both activity coefficient for the liquid and fugacity coefficient for vapor. So in reality, we are going to use this one in our course discussion, in homework, in probably in the coming exam. Very likely we are going to pick up the first or the second, not the most general case. So then moving forward, if we are looking at the liquid vapor phase diagram out of chapter 13, we have lots of plots, and we want to take a look at how we are able to actually produce those plots. One is, of course, using the experimental measurement. We try to monitor the temperature or the pressure, and we try to measure the liquid and vapor composition. And we try to carry out this from the whole range of x would be 1 to 0, y would be going from 0 to 1, then we try to have the complete plot. Okay, so here the purpose is if I know how to calculate at any known single condition of liquid or vapor, then I should be able to repeat the calculation trying to have the liquid vapor phase diagram. So that will be the focus of our discussion for today. So, like we discussed last time, if we think about the equations we are going to have for the route rule, where we are going to have low pressure, have the ideal solution, This would be the simplified equation. So we have this Pyi would be Pi z xi. Okay, then we write down the two equations for both components, and we shall have the other two equations available to us. And this is also a very useful equation, Antonio equation, to calculate the saturation pressure with a known temperature value. Okay. So for our discussion in the four types of VLE calculation, we are going to stick with the Rauch rule. And if we have to deal with more complicated liquid mixture, then we need to modify. We need to modify the liquid phase, or we have to modify both liquid and vapor. Then the calculation will be a little bit more complicated. So over there, for example, if we have to deal with the liquid mixture as the non-ideal solution, then we have to use the activity. And I hope you can see where we are able to receive those activity coefficients. We shall recall those excess Gibbs energy and those developed modules to help with the activity coefficient calculation. So this is why all those modules, Wilson, the Margol's equation, they are always trying to express the activity coefficient as a function of the liquid composition. And the coefficient should be expressed as another function of the temperature. So if that is the case, we need to add the other two equations and then combine all those previous equations. Say y1, y2 would be 1, x1, x2 is 1, and then still this is the Antonio equation over there. Okay. So that would be the limit of our discussion on our exam. I want to point you to this example we had in the textbook. So try to take a look at the example problem of the textbook. So now let's start to have the first type of discussion. Suppose we know the temperature. Suppose we know the temperature. And basically, if we know the temperature, we should be able to construct the complete PXY diagram. So let's try to take the first example. If I know the X1, so basically you need to figure out that X1 goes to 0, 0.1, 0.2, 0.3, and then all the way to 1, then you should have the complete PXY diagram, right? So here we are using the first point to illustrate how we are going to calculate. So in order to calculate, so here is knowing the temperature and liquid composition, we need to figure out the corresponding pressure of the total and the vapor phase composition Y1. So if this is the case, then like we discussed, this would be in the region of the Rauch rule. To illustrate the discussion, then firstly, we write down the two Antonio equation. If I know the temperature, then I know the P1 set and P2 set through the Antonio equation. And now if I know X1 and X2, then from the two equations, the general VLE equation, in the simplified form, I know X1, I know X2, P1, and the P2 set would be known to me. I don't know Y1, I don't know Y2, but at least I can quickly calculate if I add the two equations on both sides. So this is P, Y1, Y2, P1 set X1 plus P2 set X2. So known, that is also known, X2, P2 set would be known, Y1 plus Y2 would be 1 always. So from there, I figure out the total pressure. Okay. Now if I know the total pressure, I pick up any of the two equations, then I can calculate Y1 or Y2. right? So that means if I know the temperature, if I know the x1, then of course x2 is known. And then I'm going to calculate P of the total, and then I will calculate y1 and y2. Okay? So knowing the temperature is really convenient. Also, like I mentioned, in reality, we call this type of calculation as the bubble pressure calculation. I hope you still recall last lecture we mentioned uh, if we are moving from the liquid phase, right? If we are moving from the liquid phase to the vapor, then at some point we are going to have the first bubble. And that corresponding pressure, when we are going to have the first bubble, is called bubble pressure, or we call this type of calculation is the bubble pressure calculation. Okay. And also, if I simply give you the temperature and a system of interest to us, then you should be able to repeat those calculations and try to figure out the complete diagram of pxy. Okay, so knowing the temperature, we're able to calculate the pxy diagram. Right, so this is the first type of calculation. Let's try to look at if I know the vapor, that how do I figure out the corresponding liquid? So this is the type of calculation. We know the temperature and we know the vapor. Okay. So very similarly, if this is the temperature, then we know P1 set, P2 set. If I know the Y1, then of course I know Y2. We need to figure out one is P total, one is X1, X2. Okay. So now if you look at the, still this is always the starting equation. If you have the problem statement, or if you can justify that the Raoult's law is a good equation to use, then always write down the two equation over here. Then we need to somehow get rid of the x1 and x2 to calculate the p total. Then we can simply manipulate the equation. Now we express x1 as a ratio of py1, p1 set, similarly for x2. Then you can see that by adding the two equations on both sides, you're going to have py1 over p1 set is plus py2 p2 set. That would be 1 because x1 plus x2 is always 1, right? And we know p1 set, we know p2 set, we know y1, we know y2. So over here, we are going to solve for p total. And then just pick up any of the two equations, you're able to solve for x1 and x2. All right? And here we are, yes?
Do you always do dew point calculations when y1 is known, but bubble point calculations when x1 is known?
Yeah, so that is suggested by the name. If we are moving from the vapor, right? Vapor, this is why we know y1. If I know the vapor phase, I want to figure out the liquid. This is the calculation of figuring out when would be the first liquid will appear. So this is why this is the dew point calculation.
Thank you.
Okay. So this is the calculation with this diagram. For example, if I it's not easy for me to show the complete diagram, but let's try to see. This is the temperature. So this is the temperature as a y-x, and here we are going to have x1 and y1 because we have two lines. One is for the temperature and the vapor phase, the other is temperature and the liquid phase, right? And simply it's one dimensional, no, it's a two dimensional, then we need to fix the pressure. In reality, we should be able to have this is say x1, y1, this is temperature, and we should be able to have this as pressure. So if you are interested in the three-dimensional diagram, then here you go. Otherwise, if we are interested in, for example, if this is the T y1 calculation, then you can see that using this example, this is the condition D is in the vapor phase. It's in the vapor, it's superheated vapor over here. Then we are interested when we are going to figure out the point C or condition C. So there we are going to have the equilibrium, and we are going to have the first liquid drop. So at C, we are going to have liquid and vapor. For the liquid phase, we are interested in figuring out x1 and x2. For the vapor phase, we need to understand y1 and y2. Okay. So now if you look at the phase diagram, we have those values available to us. So this corresponding value of 0.6. So we are reading this T y1 diagram. So that is y1 would be 0.6. All right. And the corresponding equilibrium liquid phase, this is Tx1, is this condition C prime. So that is how we are going to read the value over here. I don't know what's the value. Let's say it's 0.45. Then this should be the x1, corresponding x1 value. All right. So if I know x1 and x2, then of course y1, y2 will be known to us. Okay. So the way we construct the diagram is indeed we are going to carry out multiple calculations. And in the end, we are going to connect all those dots. X1, Y1, X2, Y2, so on. So this is how those phase diagrams are constructed. Any problems so far?
I just keep going, in my opinion. Like I'm good, but lots.
So you can see that with the previous three slides, we are able to discuss the two types of vapor liquid equilibrium calculation. So now let's move on. How about if I know the pressure? Now in the vapor phase, we know the total pressure. We know the Y1. So we are moving from the vapor and we need to figure out the liquid composition. We also need to figure out the temperature. So this is, again, the dew-point calculation, moving from the vapor, trying to understand the liquid, okay? So this is why this is the dew-point calculation, and we need to figure out the temperature. So as we had problems before, whenever we need to figure out the temperature, this is always a challenging problem involving the iteration. And here, it's still the same case. So if we try to look at the calculation, or if we try to examine what would be the known value to us, let me try to save this first. Otherwise, it's really slowing down. So this is always the first equation we try to write down, and at the same time, we are going to have the Antoine equation. It's always available to us. So we know the P total. We know Y1, we know Y2, but we don't know the P1 set. We don't know the X1. Of course, X2 is 1 minus X1 is unknown, P2 is unknown. So we are going to have 4, but we can reduce X2 as 1 minus X1. So essentially, we are having 3 unknown parameters out of 2 equations, right? So this is why we need to run the iteration with the help of Antonia equation. So let me try to walk you over the general procedure. So here the temperature is not known, but we know the pressure, and the pressure P total will be contributed by P1 and P2. Okay. So over there, we try to run the limit approach analysis. Let's try to say, well, how about the total pressure is contributed purely by P1, which is, I'm going to use P total for component 1. Okay. And then over there, I'm going to have the T1, assuming the pressure is completely from component 1, because the A, B, C, those would be the coefficients with respect to each chemical species. So if I look up the A, B, C value for component 1, and I try to assume that the P total is purely coming from component 1, and I can figure out the temperature. Okay. Secondly, I'm going to assume the P total is completely coming from the component 2. So over there with Antonia equation, I'm going to use A, B, C values for component 2, and I'm going to figure out another temperature of T2. And I understand that with the mixture that shall be in between that 2 extreme cases. So that means my temperature shall fall T1 and T2, assuming T2 is greater than T1, all right? So that is the knowledge I can have out of the limit analysis. And then the other case is, well, I need to somehow simplify the calculation from equation 1 and 2. And a quite common trick is if we try to starting from this equation, I have the y1, y2 value. So I'm trying really hard to somehow get rid of the x1 and x2. In other words, I'm trying to express x1 and x2 as some function of y1 and y2. And the convenience is now if I have this 2 equations for x1 and x2, I add up that 2 equations, that shall give me 1, because x1 and x2, the sum is always 1, and that's on the right hand side. Okay. So over here, I know P total, y1, y2. I still don't know P1 set and P2 set the exact value because temperature is not known to me. So over there, let's try to run one extra step. I know this is not easy, but that is the typical trick we try to have. We try to separate at least one unknown parameter out of the equation, although, you know, both P1 and P2 sets are unknown to us right now. So we try to express P1 set as the function of the right-hand side. So there you can see that we know P, we know Y1, we know Y2, and we need to somehow figure out the ratio. So there we have this ratio. So that is a hint that if I don't know the exact value of P1 set, P2 set, what about if I know the P1 set and the P2 set, their ratio? So this inspires us to look at how we are going to manipulate and figure out the P1 set and P2 set ratio. And that's a common trick in this type of calculation. So if we start the Antonio equation, and as I mentioned, those would be the A, B, C value. So you can see that those values are species dependent, right? For each component, they will have their corresponding ABC values. So if I look at the two equations, then I try to add up the two equations. So if I add up on both sides, this is log P1 set plus log P2 set, which is log, no, I'm actually not add up. I try to subtract this. So this is P1 set over P2 set because I need to have the ratio. Okay, not their product. And then reorganize the other term. This is indeed the temperature. So that ratio is indeed depending on the temperature. So over there, I'm ready to start the iteration, which means I know the temperature by the first step. So from the Antonio equation, from the P total, I can try to figure out the temperature range, T1 and the T2. This is step one. Step two, out of that temperature range, I try to have the T gas. And then, so it's still from T1 and T2. You can basically pick up T1 as the initial gassing and try to go from there, or any value between T1 and T2. Then we are going to evaluate this P1 set, P2 set. This value with the help of that equation over there. So the convenience of having this value is now moving forward at this temperature gas. I know P1 set and P2 set, Y1, Y2, P total, they are known to us. So from there, we can calculate P1 set. Okay. If I know P1 set, of course, this is under the temperature gas, then I can move forward to the fifth step. Now I can use log P1 set is A minus B T plus C. Now I can calculate. Now this P1 set is known from step 4, and I can calculate temperature. Okay. So now I have the, that means from the gas temperature, I'm going to calculate the temperature. So this is how you are going to run the iteration until the value is exactly the calculated value as output. Then that's a convergence, and we will stop over there. Okay. So this is how we are going to start with the initial gas, and then eventually we are going to figure out the temperature. Now, if the temperature is known, then we are able to figure out everything. Because now if the temperature is known, we are going to able to calculate this P1 set, the Antonio equation, the exact value, right? Then the P total is known, Y1 is known, then this P1 set, we calculated the value after knowing the exact temperature, then the X value should be available to us.
And you would expect us to do this like on Solver, right? Or something like that, not by hand.
No, I would strongly discourage you from manually calculating those.
Okay.
So recall that the previous homework or examples we had involving temperature calculation, even for the I believe for the chapter 4 for the heat effect, we need to somehow run iteration and figure out the temperature. So the idea is exactly the same. Okay.
Yes. Thank you.
Yeah. So here the two steps are worth revisiting. One is how do we figure out the temperature range? We try to use the known P total, and we try to, again, using the limit approach analysis. That is really, really beautiful over there. And then the other is we need to realize that the P1 set, P2 set, we cannot figure out their exact values, but knowing the temperature, we are able to quickly figure out their ratio, right? So that is how we are going to reduce the calculation and how we are going to run the iteration. So step one is very interesting. Step 3 is also interesting. Okay. So moving forward, so this is a so-called dew-point calculation, meaning we are moving from the known vapor phase and try to calculate the liquid phase. And then you can see what's coming next. The next is we know the P, not the temperature, but now this time we know the liquid phase, and we need to figure out the temperature and vapor phase. So I hope the idea will be quite clear to you now. So it's still first step, using the P total, try to figure out the T1, T2, the temperature range. Secondly, we need to reorganize. We need to somehow figure out the P1 set, P2 set at the initial gas, right? So over there, if we start with the general equation, this time we know x1, x2. So here we try to somehow get rid of the y1, get rid of the y2. And that's how we try to add up the two equations on both sides. Now you can see that we get rid of y1, y2. And from that equation, we try to reorganize. Still, we want to manipulate the ratio of P1 set and P2 set. So over there, you can see that now, for example, we try to express this P2 set as a ratio of the P1 set and P2 set, very similar to what we did a minute ago. So this is known, x2, x1 would be known to us, and P1 set, P2 set, we are going to start with their corresponding Antonio equation, and we have that equation of 3, no, equation of 2 over there. So they are starting from the temperature gas. You are going to, starting from temperature gas, you are going to have the P1 set, P2 set ratio. Then over there, you are going to have the P2 set. And then if you know the P2 set, you are going to calculate the T over there, and then try to calculate the T gas and T. Try to run the iteration until you reach the convergence. Okay, and if you know the temperature, then everything should be much clearer. If you know the temperature, then this is P2 set, P1 set, exact value will be available to us. Then just pick up any of the Routh-Rowe equation, and you're able to figure out the y1 and y2. All right. So I hope if you recall, suppose we are always living in the low pressure region, then we should be able to calculate the exact PTXY diagram. Okay, and that's why you need to read, you need to go back and read chapter 13 again, looking at those various diagrams provided to us, and think about, if I have to construct those by myself, how do I start? Okay, so this is the fourth calculation we have. And then lastly, I want to show you this diagram. It's not easy to read, but I think this is coming from the the previous chapter. Yeah, this is chapter 10. So over there, if you recall, we mentioned that in the petroleum engineering, they are interested in the so-called capital K. And you can see that they are sort of using the same general ideas of calculating the diagram. For example, if I know the temperature and the Y, and then I can calculate the P total and the X, right? And from there, I just need to go one more step to construct this slightly different diagram, which means YI and XI diagram. This is called capital K diagram of the petroleum engineering. Okay. Or if you go from the if you go from yi p total would it be xi pi set. This is on the Rawls law. Low pressure ideal solution for both vapor and liquid. Then of course yi over xi shall be pi set over p total. Okay, and this is how you are going to construct those kind of diagram. So indeed, in chemi and petroleum, those would be the P, T, X, Y, or even K. Those would be diagrams we might be interested in. And I hope now you feel confident that we are able to construct all those by hand or using some software. Okay. So coming back, this is the summarize of those generally simple calculations, knowing temperature or pressure, knowing one phase, whether it's liquid or vapor, then we should be able to figure out everything of the whole system. Always keep in mind that we are looking at this liquid vapor as mixtures, say a binary. Okay. So that means for any system, if I know their pristine properties of ABC values for the Antonio equation and maybe some other property, I should be able to calculate everything for the whole system. I can calculate and predict at equilibrium what would be the distribution of liquid and vapor, and in each phase, what would be the composition for various components. Okay. So let's try to save the flash calculation to our Thursday lecture. But here I want to quickly go over a few things with the class. So the VLE calculation is super duper important for chemie, and many processes are indeed depending on those values, those curves, and we try to manipulate the manufacture condition, whether further increase the temperature or reduce the pressure or try to add more cheap components so that we can drive the equilibrium to our favored direction. So this is indeed very important, although we are only spending on a few lectures. But I need to convince you that the whole semester, our discussions were simply to get us ready for this calculation, which is again my favorite equation, and the T-shirt project, as I mentioned. So this is always about the So we are spending the whole semester, more or less the whole semester, to prepare us this equation and how do we move forward. And as I explained, this is why after thermal, you are going to have the absorption. No, you are going to have the separation class, right? The whole separation class is also built on this equation. Okay. So some other extra notes. I hope the class is taking advantage of the resources available to you. I want to mention this because I know that not all of you would be aware of the resources available to us. I want to mention a few things. One is book. The other is software. So you know that through the OU library, we are able to download lots of technical, even textbooks freely available to us by various publishers. So here is one example. This is a book from Springer. And you can download either from the general Google search, or if you go to the library and log in using your unit ID, then you should be able to download lots of books. If you search Fresh or Thermodynamics, those books are freely available to us. I hope that you are interested in taking advantage of those resources.
Can I ask a question?
Yes, please.
What about software? Because I only use Excel, but is there any other software that can help us with this class?
Yes, for the class, we are kind of limited by the time and the format of the exam, but I think there's no limitation to your understanding or to your way of your professional career development. So we know that we are using Excel for most classes, but I hope you are open to other opportunities, say MATLAB. That is actually a very expensive license if you have to purchase by yourself or by a small company. But OU has a site license, so MATLAB is free to us. The other is, for example, Aspen. Right. So I have one slide to show you how we can run those activity coefficient or even the VLE calculation purely using software. So what we have discussed is the theory behind those softwares. So Aspen is also very expensive, but OU also has a license. I don't think it's available to us by default, but if you email OUIT, you could request for the Aspen license and have some technician to install that on your laptop. So those would be the kind of, to my knowledge, it's part of your tuition. So you need to somehow figure out whether you want to take more advantage of the educational resources freely available to you. Okay, and that's indeed why I want to add those slides and I want to bring those resources to your attention. For this course, coming back to Manu, your question, we don't have time to go over all those details in software. I'm always thinking about having one elective course in the near future to run the VLE calculation or thermal with software. But I'm
It's a brilliant idea.
still collecting those materials. I hope that in 1 year or two, I shall be able to provide that elective class. Okay, so this is the first slide, and the other information is this is indeed the first time I started to encourage students to use Excel or use software for the exam, for the homework. In the past, I provided those examples, but we try to have those calculations manually, even closed book and closed notes. So I think now this might be the only positive part for this pandemic. We need to think out of the box and try to figure out a way to learn a little bit more. Now we are at home with everything online. So this is why I also want to encourage you that if you try to do it by yourself, say the flash calculation, which is quite time consuming and challenging compared with the 4 types of calculation we just discussed. I hope that you are interested in always adding some code, or maybe you can add MATLAB, right? You can add Python. Try to figure out if from the internet people have already figured out the smart way to calculate those problems, or any general code, general software for those calculations. I have to say that we have to learn the theory, no matter how. But once you overcome that kind of barrier of the uh, theoretical understanding and move forward, you are not limited by calculating everything manually or even use a simple calculator. You should think about how I can calculate automatically and how I can easily adjust the parameter, say temperature and pressure is changing, or I'm going to add another component. So you can see that no industry would be available if we have to calculate all those manually. So there must be some automatic way of adjusting those parameters. So this is why I hope moving forward you can somehow develop your curiosity along those code and automatic calculations. So here I was providing you two very general examples that if you run this Google search, those would be the available uh, resources to you. So this is based on MATLAB, and this is the chemical, how we can do the calculation. And that's indeed how I figured the Excel. I'll share in a minute. This is the other slide I want to share with you. I know that we don't offer Aspen Plus as the elective, which is a shame. But this is a very useful software for CAME. And especially if you are interested in understanding a little bit more of Aspen Plus. So here's a book by Stanley Sandler. He's a faculty from University of Minnesota, a well-known faculty in fundamental research and thermodynamics. So he put together this very nice step-by-step guidebook, introduction level of book of Aspen Plus. And if you look at the snapshot I took from the outline, so you can see that this is about vapor liquid equilibrium calculation using activity coefficient models. Okay. And this is a vapor liquid equilibrium calculation using the equation of state. So that's exactly what we covered in the past a few lectures. I really wish we have time to move on to those discussions using software, but the time is really limited. But still, I want to bring this information to your attention, so some of you might be interested to see if you can have this book and do a little bit more reading to see what would be the opportunity in the industry. Now, if I understand the activity coefficient model and I understand how to run all those calculations for an equation of state, say equation of state, I shall have this, right? Then I can run more complicated calculations. For the activity model, then I'm going to have this. And if I combine the two, then I can solve any general challenge involving the mixture and the equilibrium. Okay. So lastly, I think I'm missing one slide. So the following diagrams I took from the Excel file I shared with the class. There you can see that this is the so-called bubble line. So this is knowing, for example, this is the pressure, right? This must be coming from knowing the pressure of the total, and this is the bubble, so this is the vapor. Then this must be coming from the knowing the liquid. Then we can calculate the temperature. We can calculate the Y, right? So for the blue line, then we must go from the vapor, then we are able to figure out the liquid composition. Okay. So the Excel file. So this is the interesting Excel file, and let's try to open the Excel. I'm going to stop sharing. So those are the next few slides. They are coming out of that Excel file, I believe, when I was uh, manipulating, having some fun out of the Excel file. So this is how we are still trying to stick with the vapor liquid equilibrium, but we are moving to the upper level. So we cannot assume the route rule for the, especially for the liquid phase. Now we need to calculate the liquid as the non-ideal mixture. So if this is the case, then I have to calculate the activity coefficient. Okay. So let's try to open the Excel file, and I just need 2 minutes to quickly show you, in case you have not tried to play with that. That's the Excel file. So that's a quite nice Excel file prepared by the chemical, the website, and you can see that they have 4 different tabs. One is with the Wilson equation. This is the activity, one of the activity models we discussed, right? One is the NRTL. This is also one of the activity model we discussed, and the UNIQUAC. That's also a very popular activity model we discussed. And I believe this is a database. All those, if you are dealing with mixtures out of that database, then all the boiling, freezing point, critical, or the omega value, so on, and Antonio equation values should be available to us. So you can see that it's sort of straightforward, and it's very nicely prepared. So this says if we need to select the pair, so this would be the composition of, say, this is now using the Wilson model. Then first of all, you need to think about what's the theory of the Wilson model. Secondly, we need to identify this is the propanol versus water, right? And then we try to plot this as a function of propanol. We can also say, if we are going to change that, we are going to generate the plot in the function of water. Then you just type water, then you are going to change the resulted TXY or PXY diagram. This is one. The other is you can easily manipulate the pressure. So that is the total pressure available to us. If we try to change the pressure, then you're going to change the curve. This is the TXY diagram, and temperature as well, right? If you change this to any value, let's say 100, then you are going to modify this slightly, just shifting this a little bit over there. So this is the other. And then you can see that they are just listing all those values. Like I mentioned, utilizing X from 0 to 1, then what would be the corresponding value from the Wilson model calculation. Generally, we are able to calculate using those equations and manually figure out, but the Excel file is quite nice. And I believe we can change it. Let's try to change. If this is 3, no, I don't think that's available. What is that? I have no idea. I hope that, you know, if we type 1, 3, then we are going to change that into the corresponding components. But I think that's not available because that's the kind of hard coded in the program. Anyway. So moving to the other model, then it's exactly the same. You are able to pick up what would be the component, and using the NRTL model, how you are going to construct the TXY diagram. And that's indeed what I had in the slides as a screenshot. Okay. So I hope you might want to take a look at those Excel file and try to figure out maybe even how they implement that, how they connect those values and define the equation behind the plot so that you can quickly have those diagrams. Okay. So I think that's all I want to discuss for today's lecture, and we will move on to the flash calculation this coming Thursday.
Okay. Thank you.
Thank you all.